this set of notes, we're going to continue our discussion of hypothesis testing. In particular, we're going to look at how to calculate type 2 error probabilities and sample size calculations for the z-test. Now, what I really want you to focus on in this note set isn't so much the fact that this is for the z-test, but rather the overall structure of what we do and the steps that we follow. Because if you have a good understanding of how to do this for the z-test, then you can derive from that how you would calculate these for other types of hypothesis tests, because the overall idea of what we're doing is going to be very similar. So let's start out. We're going to look at an example to help motivate these calculations. Alright, so a sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.7. He interviews 100 families, obtaining a mean of 4.8 with a standard deviation of 0.8, and we're going to test that the alpha equals 0.1, and we're going to start out by calculating beta, and if you'll remember, that is our type 2 error probability. Alright, so we've seen this example before, but let's just start out and write out what our hypotheses are. So under the null hypothesis, we have that mu is equal to 4.7, and under the alternative, we have that mu is greater than 4.7. So this is going to be a right-tailed test. Right, and so let's also look at our problem statement just to find some values that we're going to need. So the value under the null again is 4.7. We have our sample standard deviation of 0.8. We have our sample mean of 4.8, and then we have our sample size n of 100. All right, so if we're going to calculate beta, recall that beta is equal to the probability that we accept HO, and remember here, we know in the back of our minds this really means fail to reject, just makes it easier to write, given that HA is true. Alright. So recall from the last time we looked at this example, we used a rejection region. So we saw previously that we reject if z was greater than 1.282. So we accept HO if z is less than or equal to 1.282. Where our test statistic was as follows. Right? So using this information, we know that beta is equal to the probability that z is less than or equal to 1.282, given, and remember whenever we calculate beta, we do have to specify a specific place in the alternative hypothesis. So here we're calculating when that value of the parameter in the alternative hypothesis is 5. So we're given that mu is equal to 5. Alright, so now what we're going to do is we're going to kind of work backwards. We know what z is equal to, and we know that z is a function of y bar. So what we're going to do is kind of work backwards and see if we can figure out how to actually calculate what beta is equal to. Alright, so the first thing I'm going to do is substitute in what z is equal to. What I'm going to do is I'm just going to kind of rearrange this so I have y bar by itself on one side of the inequality. further, we know that n is equal to 100, and we're going to use our plug-in principle, and we know that sigma is approximately equal to s, which is 0.80, so we can plug those values in, and if you plug those values in here, we end up that beta is equal to the probability that y bar is less than or equal to 4.8026, given mu equal to 5. All right, well, this is a probability that we can find. Given that mu is equal to 5, we have the following. We know that y bar is going to be approximately normal. With mean equal to 5 and variance equal to sigma squared over n. And further, we also know that z, which is equal to y bar minus 5 over sigma times the square root, divided by sigma divided by the square root of n, is going to be approximately a standard normal, or a distributed standard normal. Okay. So we can use this information to then help us find beta. And again, keeping in mind the reason that we're standardizing here, this is more, back in the day we had to use standard normal tables. It was much easier to find areas or probabilities from standard normals. So that's why, we typically see these things standardized so we can work with the standard normal. Since, we have the computing power now, we could just directly work with the sampling distribution of y bar to find this value. And so what I mean by that is we could actually just find this probability right here using R, because we know the distribution of y bar is this. So just keep that in mind. I am going to work through the full process to show, when this is standardized, how we go about finding these, because historically that's generally how these are shown. But just keep in mind, we don't necessarily have to do that. And I'll talk about that more here just a little bit at the end. So here, again, we have the probability this is less than 4.8026 minus 5 divided by sigma over the square root of n. Again, this is all conditional on mu being equal to 5. Now, since we have already incorporated that mu equal to 5 into the standardization, I'm actually just going to drop it from the probability. So this is equal to the probability that z is less than or equal to 4.8026 minus 5 divided by 0.8 divided by the square root of 100, which in turn is equal to the probability that z is less than or equal to negative 2.468. And again, here we could use R, a calculator, any software that you want to, and we find this is equal to 0.0068. So that is our probability of a type 2 error. Now, alternatively, what I was saying before, you could work directly with the sampling distribution of y bar. So alternatively, we do not have to convert to z. Notice from up above, we have beta was equal to the probability that y bar was less than or equal to 4.8026, given that mu is equal to 5. And we know that y bar is distributed approximately normal with mu equal to 5, and then using that plug-in principle to estimate our standard deviation of y bar, or our variance of y bar, we have 0.8 squared divided by 100. So therefore, we know the standard deviation of the sampling distribution is going to be 0.8 divided by 10. And so what you could do is then in R, work with a normal distribution which has a center of 5 and standard deviation equal to 0.8 divided by 10. And then what you would be doing is you would find the probability that y bar is less than or equal to 4.026, which is this area right here, and you would find that this area is equal to 0.0068, the same area that we found when standardizing. And so this is why I was talking about it's important, when we think about these problems, not so much to focus on the fact that we're finding beta, for a z-test, but to really understand how this relates back to the idea of the sampling distribution. And really what we're doing is our statistic that we're interested in is y bar, and we're utilizing the sampling distribution of y bar to find these probabilities. Now, in order to use that sampling distribution, we have to know, what assumptions we have and how that's going to affect what that sampling distribution is. So here we've been working with large sample sizes, so we're assuming that the sampling distribution is approximately normal or standard normal. As you probably recall from your intro stats class, a lot of times when we work with means, we will go ahead and default to working with a t-distribution, especially if we don't know the population standard deviation. We're using that plug-in principle. It's usually safer to go ahead and work with the t, but notice that the process here is pretty much going to be exactly the same. It's just you're going to work with a t-distribution instead of the standard normal distribution. And keep in mind that, as the sample size increases, the t-distribution does approach a standard normal distribution. So that's why here it really doesn't make much of a difference. Alright, so next let's look at how to calculate a sample size for a z-test. Now, keeping in mind what I was saying before, usually when we work with means, we work with t-distributions. For sample size calculation, since the t-distribution does depend on the sample size, we'll usually default to working with the standard normal anyways. Alright, so for this example, let's work with proportions just to mix things up a little bit. But again, keep in mind that the overall idea is what you really want to focus on here. So suppose we want to test the following. Under the null, we're going to set p equal to p naught, so some value under the null hypothesis. We're going to try to prove that p is greater than that value. So the question is, how large should the sample size be if we specify the value of alpha and beta for the alternative PA? So we're going to specify a specific place in the alternative. So notice what we're doing here. By not giving specific values, what we're going to actually be doing is not just calculating the sample size, but we're actually going to be finding a formula for the sample size in this example. So as usual, we're going to start with the definition of beta. And so recall that beta is equal to the probability. We accept HO given HA is true. And again, that's accept HO with quotations around it. Alright, so next, if we think about that rejection region, what we're doing is we reject the null if Z is greater than Z alpha. So therefore, we accept HO if Z is less than or equal to Z alpha. And this is true since we have the right tail test. Notice if you had a left tail test, we would actually be flipping these inequalities. And if you had the two tail test, you would actually be working with alpha divided by 2. And then our test statistic that we're going to work with, we're still going to use that standardization. Our estimator in this case is p hat. So we're still going to subtract off the value of the estimator under the null hypothesis, and we're going to divide by the standard error for that estimator. And one thing to note here is both the mean of the standard deviation and the both the mean of the sampling distribution and the standard deviation of the sampling distribution both depend on the target parameter. So what we have to do is, since both of those depend on the target parameter, this has to be the value of the target parameter, assuming that the null hypothesis is true. Okay? So using this, we're going to have the following. So the first thing that I want you to notice here is the conditional information is on HA being true, and that's because of the definition of beta. So that's why here in the conditional, this is going to be the value of P under HA. And so remember, we've talked about before, whenever we calculate type 2 probabilities, we do have to specify a specific place in the alternative hypothesis. So this is why it's so important with your subscripts here that you're really being clear. Are you considering the value under the alternative, or are you considering the value under the null? So then we're going to plug in what Z is equal to. So again, we've got P hat minus P naught divided by the square root of P naught times Q naught divided by N less than or equal to Z alpha, given P is equal to PA. So again, notice here we've got values of P under the null and the values of P under that specific place in the alternative hypothesis. So next, we want to get P hat by itself. So very similar to before when we got Y bar by itself. So the idea is, again, we're going to get that estimator by itself. And the reason that we're doing this, and I didn't say this in the last example, but the reason for this is P hat is the random piece. So this goes back to that idea of keeping in mind that the estimator is random, everything else is fixed. So when we're talking about that probability statement, what we're doing is we're isolating the piece that's random, and then we're going to utilize the distribution of that random piece, assuming that we're in that specific place in the alternative hypothesis. So that's why we start out with it standardized, because when it's standardized, we can utilize the distribution of the standardized piece, which is that normal. Then we isolate the piece within that is random, and then look at the sampling distribution when the alternative is true. So you're both looking at the distribution assuming that the null is true and that the alternative is true. Right? So when we do this, we have that beta is equal to the probability that P hat is less than or equal to P naught plus Z alpha, P naught, Q naught divided by N, again given that P is equal to PA. Okay, so next that we're going to do is we're going to re-standardize. So here we started out using that piece, again assuming that the null was true, which occurs not in the conditional piece of the probability, but in this piece. Different colors so it doesn't get confusing. We isolated the random piece, and now again we're going to re-standardize P, or P hat rather. And again, it is at this stage that this second standardization, we don't actually have to do this piece because software will allow us to work directly with the sampling distribution of P hat, but this is done so we can then, again, work with the standard normal if we needed to for computation purposes. So recall that when P is equal to PA, we have that P hat is distributed normal, PA, and then the variance is PA times QA divided by N. So again, you've got to keep in mind that now that we're assuming that we are in that specific place in the alternative, when we think of the sampling distribution of P hat, both the mean and the variance or standard deviation depend on that value of P. So we have to make sure that we're matching those up. Alright, so then that gives us that beta is equal to the probability p hat minus pa divided by the square root of pa qa divided by n less than or equal to p naught plus z alpha times the square root of p naught q naught divided by n minus pa divided by the square root pa qa divided by n. And again, this is all given that p is equal to pa. So just a couple things to note here. Note that this term is z. And then also notice that this term right here we can split into two pieces. And so if we do that, we have the following. Okay. Now notice at this point when we look at beta and we look at this probability, notice that there are no p's left in here, and that's again because we've already basically incorporated that condition that p is equal to pa. So at this point we can drop the condition, and so this is going to give us that beta is equal to the probability that z is less than or equal to p naught minus pa divided by the square root pa qa divided by n plus z alpha times the square root of p naught q naught divided by n divided by the square root of pa qa divided by n. Okay, so next thing to notice is this entire piece. So all of this. Notice this is actually an endpoint. So if we think of the distribution of z, there is some endpoint that this thing is going to be equal to. So this is really just some endpoint, and we know that the probability of z being less than that endpoint is going to be equal to beta. So this is an endpoint that we could solve for. And so we can just denote it with negative z beta. And again, this is because the following. So if we redraw our picture here, we have 0. If we have a negative z beta, we have a positive z beta. What we're saying is we have beta area here. So due to the symmetry, if z beta has area beta to the right, negative z beta has area beta to the left. So that's why we have the negative there. And so this is going to give us the following. So we're just setting that endpoint equal to that piece of the probability that we said it was equal to up above. And Next, the last thing to notice here is notice that this is a function of n. Remember, the whole reason we're doing this is to get a sample size calculation. So the next thing that you would do is just solve this equation for n. And so I'm going to let you do that on your own. But if you solve this equation for n, you should get the following. So again, the big idea here isn't so much the calculation for this particular example, but it's more those big ideas that it incorporates. Notice in order to do the sample size calculation, we're both considering the sampling distribution of our estimator under both the null and the alternative. That's why in this particular one we see z beta and we see z alphas. So in other words, those are different endpoints from those sampling distributions, depending on what your allowable type 1, your type 2 errors are. We also see that this formula is going to incorporate pieces of the parameter or the target parameter both under the null and the alternative. So for sample size calculations, we do have to specify where in the alternative we believe the target parameter is. So in practice, I mean, that can be difficult, and it does have to, we have to guess for that. But part of the reason is if your target parameter, the true value of it, is very close to the value under the null, you're going to have a pretty big sample size to pick up those small differences. Where if the actual value of the target parameter is far out in the alternative, you need far smaller sample sizes to pick that up. And so this is why this formula has to include both of those values. Alright, so summarized here, this is the sample size for testing both for a population proportion and for a population mean. You could get the population mean formula very similar to what we did before. Alright, so as we've alluded to previously, there is a relationship between hypothesis testing and confidence intervals, and so we have that relationship here. So previously we showed that the formula for the confidence interval is as follows. We also showed that if we were going to test this hypothesis, we use our test statistic and then our rejection region. And it ends up that one of the reasons in the notes we focus on showing the rejection region is if you look at the rejection region instead of the p-value, it becomes much more clear that relationship between confidence intervals and hypothesis test. So considering that rejection region, notice we fail to reject the null when we are not in the rejection region. So here we have not in the rejection region. And so what we're going to do now is just rearrange this inequality. So the first thing we do is we know that z is equal to our standardized estimator. So notice that's what we've plugged in here. And then when we think about a confidence interval, we know that the confidence interval, the way that we looked at before, we want the parameter in the center. And so what we do here is get the parameter under the null hypothesis by itself. So then we see we have our random pieces. Well, the way this is written, this isn't actually random because they're not in a probability statement, but we have our estimator on either side. And so notice this is the exact same as the confidence interval that we would calculate. So what this suggests is we don't reject the null in favor of the alternative if theta naught is in the confidence interval. And this makes sense because our confidence intervals give us a range of plausible values for our parameter. So if the value under the null is inside of the confidence interval, that suggests that it is a plausible value, so we wouldn't want to reject that value. Alright. So we've talked about p-values in the past. I assume that most people are pretty familiar with p-values, so I'm not going to spend too much time on them here. If you need more information on them or you need more of a review, let me know, and I'm happy to provide more of a review. But we talked about how rejection regions essentially look at the endpoints under the distribution. P-values give the exact same information. They're just looking at the area under the distribution. So the p-value, or obtained significance level, is the smallest value of alpha for which we reject the null based on our data. And so by definition, we reject the null for all values of alpha greater than p, and we fail to reject for all values of alpha less than p. Alright, so let's look at an example and just kind of briefly talk about what this looks like, again, in terms of that sampling distribution, assuming that the null hypothesis is true. Alright, so here's that example that we've seen several times. A sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.7. He interviews 100 families, obtaining a mean of 4.8 with a standard deviation of 0.8. We're going to find the p-value for the statistical test performed. So here we have our hypotheses we've seen before, and we have our appropriate test statistic. So notice that our test statistic here is a z. Often the name of the test statistic corresponds with the distribution. So here our test statistic is a z, so we know that corresponds to a standard normal distribution. So when we talk about finding the p-value, really what we're saying is if we draw the distribution of the test statistic, which again here is a standard normal, so we have a normal distribution centered at 0 with a standard deviation of 1, what we're doing is we're looking at our test statistic and placing it as an endpoint on that sampling distribution, and then the p-value is going to be the area under that curve, which is more extreme than that endpoint. So this is where the tail of the test is going to become very important. Since this is a right tail test, when we say more extreme than 1.25, that is going to go to the right. Of course, in a left tail test it would go to the left, and a two tail test would go on either side. So this area right here is the p-value. And then again, to find this, we would use software. You could use a calculator, you could use a table, but any of those. And so if that area is small, notice that as you go further into the tail of that sampling distribution, that area is going to shrink. So that's why small p-values provide a lot of evidence, because it suggests that you are further out in the tail of that sampling distribution, assuming that the null hypothesis is true. So in other words, we've gone out further in the tail. The probability of observing that value of the statistic, assuming that value of the parameter, is very unlikely. So that's why small p-values are going to provide a lot of evidence. Alright, so the last thing we're going to look at in this note set are small sample hypothesis tests for mu. And so I've alluded to this a little bit earlier. Most of the time in your intro stat class, if you were working with means, you probably use a t distribution instead of a z distribution. And part of the reason for that is if you have small sample sizes, or if you know the sample standard deviation instead of the population standard deviation, we'll often use a t distribution. So we've developed approximate tests to use when our sample sizes are large. To derive small sample tests, we need to add the assumption that our data come from a normal population. And so do keep in mind, if you're using a t-test, you do have to have that assumption. So if that assumption isn't reasonable, you probably need to use a different kind of test. So here we're going to use this test statistic. Notice here that the test statistic is very similar to when we worked for the large sample test. Here's kind of the summary, and I'll let you read these on your own. And then we've got two examples here. So again, I'm going to just let you read through these examples on your own. If you have any questions, let me know. But you're going to find that these are very similar to when we looked at the large sample hypothesis test. Really the only difference is we're finding our rejection regions from t distributions instead of z distributions. Other than that, there's not really any difference. Same thing is true when we look at the difference in means. Again, we're going to derive our test statistic using that t distribution. So when we talk about our rejection regions or our p-values, they are going to come from a t distribution instead of the standard normal. And I have another example of that for you here. So read through those on your own, and if you have any questions, please let me know.